Nice. Yeah, welcome. Cool that you made it to my talk. Yeah, I'm going to talk a bit about how I'm planning to not break all your dApps in the future. The focus is actually on the not in the title that I handed over to the Gnosis team or the conference team. We forgot the not, so the focus is really on the not. We don't want to break stuff in the future, and this talk is mostly about how we are planning to achieve that. Next topic, in the printed out agenda, or if you looked last week at the agenda, you might have seen that the talk is about distributed sequencing. My colleague who wanted to do that talk originally couldn't make it in the end, so I'm taking over and I changed the topic to talk about data migration. I think it's also going to be interested, so please stay here. But you have to wait for the distributed migrated sequencers for some other conference. Yes, so now I already skipped a bit. Yes, short intro. I'm Paul. I'm working as a developer for C Labs in the blockchain team. We're basically taking care of a guest fork that runs the Celo blockchain. And yes, a short intro into Celo. Some people might know it, some people might never have heard of it. It's an EVM-compatible chain, basically, and it was one of the first chains that was carbon neutral. So we achieved that by implementing a proof-of-stake system in the days when Ethereum was still the proof-of-work chain. And this proof-of-stake consensus is based on the IBFT protocol. So besides this lower energy usage, that gives us some nice properties. One of them is one-block finality, which is really beneficial for people developing applications on top of the Celo blockchain, and also for users because they don't have to wait for confirmations and so on. And together with a current block period of 5 seconds, we think that's really user-friendly, allows a lot of use cases that have been hard to achieve on obviously Bitcoin with its block time from forever, but even Ethereum before. We think that allows some new cool things to be built. Another feature that I usually think isn't used enough and that makes onboarding a lot easier is that we have gas payments in ERC20 tokens. So you don't have this onboarding problem as you have usually in Ethereum, where people just want to send a transaction for whatever stablecoin that they own, and they have to get Ether and able to send transactions from their accounts. But on the Celo blockchain, you can just use stable coins that we offer. For example, we have a stable coin for US dollars or euros, and you can use those to also pay the gas price, the transaction costs. And obviously you need a different transaction type to do that, but still it's only used in a roughly 5% of all the transactions on the Celo blockchain, and I think it should be used more. I think it's pretty cool. Especially in the whole context of account abstraction that people are now talking in Ethereum. I think it has the same, a bigger scope, but it goes in the same direction. We're gonna make onboarding easier and allow people to not have those problems of needing to own Ether in order to send transactions. Yes, if you want to find out more, you can look at the website. It's celo.org, easy to remember. And a little shameless advertisement, on Wednesday morning, René, the head of the Celo Foundation, is going to have a talk about unlocking Web3 growth in Africa. It's going to be less on the technical side, more on the impact side, but there I think he's going to share a nice presentation. If you're interested in that stuff, please go over there. So, what are we going to look into during this presentation? First, why do I, as a developer working on the Celo blockchain, do have to care about not breaking your applications and smart contracts? And to understand that better, we're going to do a little deep dive into state handling, how is state working in the EVM, how do events work, and so on. So we're going to dive a little into the data structures of Ethereum. And after we understand that, we can look a bit into how can we migrate that state. And in the end, gonna have some questions. I mean, I've been more in the nitty-gritty details of of the protocol layer in the recent times, so I lost a bit of contact to smart contracts and people building on the blockchain. So I'm hoping to get some insights how applications look nowadays and try to get some feedback from you. What do you think is important? What doesn't make so much sense, and so on. Again, the Celo blockchain historically has been an L1 chain, but we want to align more with Ethereum, and this has different reasons. So one of the first reasons is we historically changed some protocol things like the header structure in the blockchain. We changed that, which made RPC calls horrible because some tools could work with it, other tools couldn't. So we now want to get closer to Ethereum to basically make developers' lives easier, allow them to use the tooling they want to use, and so on. But additionally, also becoming an L2 would allow us to use the additional economic security that Ethereum offers us. So there's way more TVL on Ethereum than on the Celo blockchain currently. So becoming an L2 would allow us to use that basically for our benefit and allow for different use cases than are currently possible. Additionally, becoming an L2 also might improve some of the bridging story, which is currently a bit rough around the edges. And basically there's lots of investment going into bridging around L2s, and we hope we can use some of those. So on the right side, you basically see one of our on-chain governance proposals where we asked the community what they think about this. We basically wrote a forum post about this idea to become an L2, and actually it seems like the community is quite excited about it. But obviously there are some constraints, and these are the following. So currently transactions are quite cheap on Celo, so this is a requirement, and that actually means that we have to go a bit different way than current L2s or optimistic roll-ups like Optimism or Arbitrum are doing. So they're saving all the transaction data on-chain, on the Ethereum chain, mostly as call data at the moment. But this is so pricey that we basically can't do it if we want to keep current transaction prices. The next thing that's, as I already said, really important for us is this one-block finality. And current rollups can't really do that. So we have to change some fundamental assumptions there. And we think we can get kind of like a two-stage process. So if you don't need the highest economic security, you can basically have this one-block finality. But if you want the whole economic security of the L1, in our case, Ethereum, then you need to wait, obviously, a bit longer to get that benefit too. And the last point, and this is where the circle closes for this talk, is basically we already have a chain, we have lots of users, we have a lot of on-chain contracts that are deployed, and we can't start from scratch. So we have to find a way to migrate our state to this L2. So before we look into the state itself, just some stats so you can get like a feeling about what we're talking here. So Ethereum at the end of August on a full node, not an archive node, was roughly like a terabyte of state. An archive node usually 2 to 3 times bigger, so 2 to 3 terabytes. And the Celo blockchain is a bit smaller. So end of August was like nearly 200 gigabytes of state, 20 million blocks, nearly 300 million transactions. And I was a bit surprised by that number, that there are like 722 million events emitted. So that means that every transaction roughly emits 3 events, which I found surprising because I expected it to be less than 1 in average. But nice to look into those numbers sometimes. And usually, I think Ethereum grows by a couple of like gigabytes per month, the state. Celo, obviously, a bit less. And again, all these numbers are from full nodes, so they already have some state pruned. What that means, we're going to talk about it in a bit. But now you have a feeling for the stuff we're talking about here. So how is state actually stored? I think the stuff that people think about is, like the account storage, smart contract data, and so on. So this is the first thing, and we're going to look a bit into how this is implemented in the Ethereum clients exactly. But for users and like people interacting with the blockchain, I think there's two other things, namely like transactions. People want to know, what have I done historically? What are the transactions I sent in the past? And also transaction receipts, including all the events that people or applications might use in different ways. So those three things are the things I want to focus on. And now let's look how this actually works. And I hope it's big enough. Can you read it from the back? Yeah, let me know. Otherwise, I can explain it a bit more. But basically, you see there's on the left side, we have like the block structure with the header and the block body. And then on the right side, we have some state. And those state thingies that we're going to look into soon, they have the form of a tree. So they are Merkle trees. I guess most people know what a Merkle tree is. But as a short reminder, it's like a data structure that makes it really efficient to compare state, and also makes it possible to have efficient proofs of a certain state. And it works by, you have some data blobs that you want to put into this tree, and basically it works by hashing those data blobs, and the hash of this data creates the leaf nodes of the Merkle tree. And then if you go up the tree, every node is basically the hash of all its children, and you do this until you're at the root of the tree, and that root is basically, it contains information about all the other trees, and if some little data blob changes down in the tree, then the root changes as well. So this is what we see here. This whole tree is basically stored in the header via this state root of the Merkle tree. Now we zoomed out a bit more. And we can see there's like those three parts that we talked about. The first one is about the accounts storage. Then we have like some storage for the transactions and some storage for the receipts. And let's look first at the account storage. It's called world state here. But it's the most fundamental thing, with that the state that the EVM can access. And exactly. Let's look a bit in how it works. So in the block header, there's the root of the world state trie. And this basically means that this is like the hashed version of a lot of data blobs, and these blobs are account states. So in Ethereum today, there are two kinds of accounts. There is like externally owned accounts. This is basically the stuff that you can control with your private key on your computer or on your ledger. And there are contract accounts. And again, this is like the model how it is currently working. There's talk about how to change it with like the whole account abstraction thingy. But for now, it works like this. So we have these accounts, and externally owned accounts, they basically only fill the nonce and the balance fields, and every time you send a transaction, the nonce is increased, and the balance is just like all the ether that you might own. For like contract accounts, this like code hash is also set to the hash of the smart contract bytecode that is actually stored for this account. And the important thing here is that like the nonce and the balance are mutable fields, so those can change in which each like state transition in the blockchain, but the code hash is actually an immutable field, and this is the reason why smart contracts can't be changed. So once this is deployed, even if you have a bug in your smart contract, you need to redeploy it, but you can't change the hash, and therefore you can't change the bytecode of a smart contract. So a smart contract also might have some data that it stores, and again, in this account state, we only have to store the root of like another Merkle tree, which stores the account storage. And how this storage exactly works, it's a bit like too deep for this talk. But yeah, you can imagine it's like some key value pairs with some data in a special way that makes the contract be able to access all this stuff. The next part that we talked about is the transactions. So the transactions are actually a part of the body. So light clients don't need all the transaction data. They actually only sync the headers. But we're going to come to this. They also store the root of this transaction trees. So we can imagine this like the body includes like a bunch of transactions, and this is the full transaction data, and they get put into a Merkle tree, and the root of this Merkle tree is stored in the header. So light clients can verify data when they get data from full nodes. The transactions itself, the underlying data is transaction blobs, and as you may know, there's like old school transactions, like the old transactions that one probably doesn't want to use anymore, but they're still supported. And then there's like more modern, like EIP 1559 type transactions. It's not really important, but they all get hashed, put into this Merkle tree, and stored in this transactions root in the block header. The same happens for the receipts. They are. Actually not. It's stored in the database, and just the hash of it is stored. So you can verify that it's right, but you might have to request it. Okay. So for the receipt, it's the same. In order for light clients to work, there's the root of the receipts tree gets stored in the header. So the light client might not know what the receipts are for a certain block. But when they request the data from a full node, they can actually check that the data is correct. Which, it's kind of cool that they thought about it in the beginning of Ethereum to make it light client friendly. There's another cool thing to know about receipts. So events that are emitted by the blockchain, they are stored in the receipts. So often we want to do some filtering on like a big interval of blocks, and this is, you can imagine, it's like a sequential scan on a database. So we have to go through every block and filter out all the events that are matching. And if we would actually have to go down in this tree and like check every little event, then it would become like horribly inefficient. It already is inefficient to do this like sequential scan, and there's better solutions to do that. But there's a little optimization that people put into Ethereum, and this is basically we add like a Bloom filter in the header, and this combines all the indexed event fields get basically put in a Bloom filter. Some people might have heard about it. It's a probabilistic data structure. And basically, you can have false positives, but you can't have false negatives. So that means if you see in this Bloom filter, you can check, is something matching the signature? And if you receive a yes, then that means probably there's something included that matches that signature. But if you get a no, this is not included, then you know for sure. So basically, that makes the sequential scan a bit faster by going through each block, looking at that thing. If it matches, then we have to go through the whole receipts list to check in detail. If not, then we can just skip to the next block. So now we looked at how these like three things work data structure-wise in Ethereum. And now I already mentioned that we have that there's a difference between full nodes and archive nodes. The important thing here is that usually people aren't interested in whatever old state. So as we see here, at like a certain block in the blockchain's history, there's always a link to the state root at that point. And in theory, you could query that, but often when you just want to estimate the gas price of a transaction or look at the state of a certain contract, you're only interested at the current state of the blockchain, not in the state like 1 year ago. So in order to optimize that, we can basically look which parts of the state trie aren't linked in the state tree anymore, and just remove them. And yeah, as I already told you, this usually removes the reduces the state by by a factor like 2 to 3. For transactions, we actually can't remove them. We might need them again to look at them, look at the history. And receipts also, they might be removable, but at least in Geth, they aren't. So in theory, they could be reproduced by either querying them or re-executing the transactions. But I guess also the amount of storage you could save is not really worth it, like removing them. So most of the state pruning actually happens in this world state trie, that as they call it here. So sure.
Because you were also saying that in the EVM, I can only access the state tree, not transactions and receipts.
Mm-hmm.
So transactions and receipts, I know them as state transition history.
Mm-hmm.
So for the EVM itself, they are kind of irrelevant, right? You never need them in the future. I know they are interesting off-chain for users.
Mm-hmm. No, exactly. It's more like if you want to query them, and I think that's the main reason, it's not really worth it at the moment to prune them. But for the state transition, to check that, you just only need the current block, the current state trie, and then you can check the state transition for the next block.
So I just didn't understand why then the receipts and transactions cannot be pruned when you are
I think it's not really technical reason. I think it's more convenience reasons, that first people might want to query that stuff, like transactions. Okay, what are my transactions in the past? And it would be inconvenient and probably not really worth it compared to the state pruning of the state trie to remove those. And the same with events. That at least, when I was doing stuff, it was common to, okay, give me the events for the last year of that token or whatever. So in theory, you could remove it, but it would probably make it even more complicated to people to understand, what's a full node, or it's a full node that also has pruned events. So I really can only use it to, estimate transactions or look at the current state of things. Does it make sense?
Okay, but then it makes a difference what thing could potentially break the smart contracts, because removing transactions and receipts cannot break the smart contracts because they can only access the state.
Exactly.
It may break the user interface for the smart contracts. The user interface relies on events.
Yes. So as we saw, in the header, we always have this transactions route. So in theory, if we remove them, we could ask another full node, please give me this data. But then it would become more centralized, and it's a lot more pressure again on archive nodes and so on. So I guess this is some kind of trade-offs where people actually decide, okay, this storage savings are so small and it might be so convenient for people to have that data that they don't actually remove it at the moment. Maybe it comes when the blockchain grows another 5 years that people say, actually now we can save a couple of gigabytes by removing that stuff, and we remove it for everything that's older than 2 years or something like that. Good. So now coming back to this L2 to L1 to L2 transition that I'm working on, and where we basically want to bring over our current state. How can we, in theory, do that? I see 2 ways. The first one is just do what every Ethereum client or Celo client does. We start at the Genesis block, we sync the whole chain, go basically through every state transition, check that they match what we see from the data we get from all the other nodes. And do that for a while. I think on Ethereum it takes at least a couple of days or weeks even nowadays. And get to the tip of the chain, and then we continue whatever we want to do. The other option that I'm working on is doing something that I found people call regenesis. So we basically do some kind of a snapshot of of the blockchain and remove all the history, but move the state trie into this new Genesis block. But first, let's look a bit at the trade-offs. So when we would want to sync this chain, that also means that we need to support all the historical versions or quirks of the protocol. So in Ethereum, I'm not actually sure how old it is now, but yeah, we need to support all the object formats, how the header looked like, and so on. We have to confirm to all the EVM behavior, how did certain bytecodes behave. We have to implement all of the hard forks that happened in between, even though we only want the chain to work in the current now and here. And we also have to support that for the unforeseeable feature. So the client is only getting more and more complex. And yeah, to give you a feeling of that, of course, I selected this because it shows that quite well. This is how an EVM interpreter is created in the Geth code base at the moment. So you see there's for all the hard fork that happened in the past and are about to happen, there's basically different instruction sets. And all over the Geth code base, there are those little if statements. If this hard fork is enabled, then do this. If not, do that. And yeah, you can imagine how that increases complexity for testing. From my experience, the stuff only gets worse, and you can't really remove all stuff ever because you need to support the sync process, and that means you need to run all of these code paths eventually. Another negative point is what I already said. The syncing process scales linearly with the block height, so the longer the chain gets, the longer it takes for the first sync, making it increasingly. Yes?
Sorry, a quick question. I realized I don't understand fully. So we have Silo blockchain with its own state, and we have Ethereum, and now you're talking about syncing Ethereum from Ethereum Genesis in Silo, am I right?
Not really. So now I'm talking about the general, if we would something to do in Ethereum, then we would need to support all these different.
I just want to wrap my head around, okay, if you're migrating to an L2, if Silo becomes an L2, why do you care about all the Ethereum state?
I'm just taking it as example. I could have also shown some code snippet of Celo. It looks the same, just that some of the hard forks are called differently. But what I basically wanted to say, if you want to support syncing any chain, you need to support all the hard forks and all the code that was ever, all the protocols that were ever executed during the life of that chain.
Migration, this would be the Silo history.
Exactly. Okay. So from, I think 2017 or 2018, I'm not sure. I shouldn't.
Can you just not take the current Silo state and just basically declare it at genesis of Silo L2, that, okay, this is the initial state by definition?
That's where we're coming next.
Okay. So, Russian too. Good point. We're getting there. And so the syncing takes more and more time. So ideally, for people coming into the ecosystem, it gets more and more you start this node, and then 3 weeks later, you might be synced, or something happened in between, and you have to start from scratch. So it gets more and more hard, and people are more and more using centralized providers to do that kind of stuff instead of running their own nodes. So what we are thinking about is basically what you already said. We want to do a new Genesis block, but put the state we already have in there somehow. So of course, it's not that easy. And one of the big trade-offs would be that we lose all the historic transactions and all the historical events. They would be still queryable. We could keep the old nodes running before that event and query that stuff, but it would be a bit harder for developers to, they would have to do something to query that stuff. So quick intro, how a chain is created at the moment. Again, at the example of the Geth client. So on the right side, you see one of these Genesis configs. This is basically the file with which you can create a new chain. You see at the top, there's this config thingy where you can enable or disable certain hard forks. This is kind of an old example because it only includes the really bare bones stuff. then there's a lot of stuff which you don't really need to care about. And then here, this alloc field is quite interesting because that goes basically directly into the state trie that we looked at before. So this is the way in a Genesis config to set the state of certain accounts in the state trie. So here we see for this address like C2D7, this is going to be like an externally owned account, and here we just say under this account, please create like a balance or initialize it with a balance, and that also sets the nonce of this account. So once this chain is started, then the person that owns the private key for this account will have like a balance preset in this blockchain at the Genesis block. The second account here, this is going to be like a smart contract account. So we basically say, okay, it's not going to need a balance, but we also set like the code, which will put this like EVM bytecode into that account, or hash it, like store it somewhere and put the hash in this account state. And then we also set some storage for that account. So if we would then create a blockchain based on this config, which is like something like geth init genesis.json, we would create a new block, probably number 0. And yeah, if you would start it and not create no new blocks on top of that, you would have like at least this one smart contract and this one account in the blockchain. Now, the first obvious thing to think is easy. We can basically go through the whole state that we have, these like 190 gigabytes, and just put them into this JSON file, right? Like for every account that we have, we just write like a line in this in this config.
We need to do the full state, but without transactions and events.
So we could just say, okay, we get rid of all the old blocks and just go through every account in this giant tree, which is like 190 gigabytes. Yeah. And probably, I mean, this is like a bit more efficiently stored. So if we store it in the JSON, it's probably going to be like 500 gigabytes. I'm not sure. And then we would need to import that. I guess everything would break when we try to do that. So this is kind of the first idea, but we can do like it better. We can actually go at the database level and yeah, hop over this export-import process on the way. Yeah, so I'm mostly working on the geth fork for this. So in geth, the data is actually stored in a key value database that is like underlying the whole blockchain. And so what we do there, we open this database and we're looking for the latest block in this database. And in this latest block, or in the header of the latest block, we can get the root of the state tree and store that, because this is the important part that we want to keep. We want to put that into our new Genesis file. And then we can actually go through the database, and there's going to be like these like 20 million blocks that I talked about in our database, and we can just remove them. So we just delete all the history. Have to be a bit careful that we don't delete too much data, but actually the blocks and the headers, we are not interested in them anymore. So we remove that stuff and then create by code a new block, whatever it's going to look like. We can set it up as we like. And importantly, we put this, the root of the state trie in there. So by then we have a new Genesis block that references the state that we had in the chain before, just that we removed all the history and removed like 20 million blocks. Now important to make clear is that everyone could do that. So everyone who has like a Celo node and is doing this migration, which is probably set at a certain point of time, can check this process. So it's like a tool that you can run, which is going to be enabled at a certain point in time, and everyone can verify that the new Genesis block that we are like putting online wherever is actually correct, and decide to not follow the chain if we try to build whatever backdoor in there, or change account state however we like. So this is verifiable, everyone can run it, and so nobody needs to trust us. But now we're running into a different problem. So now everyone who is running a Celo node can actually do this, but how do new people like that just want to sync with the network after this read Genesis event actually sync it? So The problem is now you can't go through the chain and apply all the transactions and actually get to the end state, but you need to somehow sync those like 190 gigabytes of data, which is not included in the chain. Or it is included, but it's not really available. So something that Optimism is working on for their superchain is basically that we extend the Genesis definition a bit. And this is like all the common stuff that's already in there, but we basically extend it by saying we also can give it a state hash. So we basically say we put a reference to that state tree in that we want to have, and the clients will accept it, saying, okay, this is the state I wanna have in the end. And for now, I just accept that I have a Genesis block and I have a reference to that hash, but I have to find out what the underlying data of this like giant Merkle tree actually is. And yeah, and then we can already use like existing protocols. So there's the ETH protocol, which actually nodes use in this P2P network of Ethereum to exchange blocks and headers and so on. And even better, the Snap protocol, which is especially optimized to sync state in Ethereum because it does like bigger chunks, so you have like less round trips, and it's in general a bit more efficient in doing that. So the procedure there would be someone wants to sync this chain. He downloads this Genesis file, which includes the state hash that everyone else can verify by using our migration tool. The client loads that, sees like, oh, I'm actually missing some state to verify the state hash, and then starts the Snap protocol to actually ask other full nodes in the network, please give me this data, and slowly rebuilds this state trie. Obviously, this whole process is not without downsides. So as I already said, we're gonna lose all the transaction and evade data, which is not nice, but yeah, you can still get it. Yeah, you can still run the nodes from before this regenesis event, which is not ideal, but it's still there. I mean, it's not lost, and yeah, it's just maybe a bit more inconvenient to access it. And building a seamless solution to access this might actually not worth it. I'm not really sure. But if you imagine like some ETH event filter query that goes over this regenesis event, you would need to split it. If you want to provide a seamless interface, you need to split it. You need to send both requests to the old nodes and the new nodes. You need to wait for their results, combine them again, and send them back to the user, which, yeah, it complicates stuff. To really make it work for every possible case is probably really hard, and I'm not sure if it's worth it. So that's something I want to discuss with you a bit later, or actually now, because so my feeling is that for transaction, I think this is like totally fine, but my questions for people working more on top of the blockchain is, do you still rely on events nowadays? Or is everyone using other like indexing solutions? The graph comes to mind. Is that something that you're working with? Would losing events from the chain history be something where you say like, okay, no way, this will never work, nobody will ever keep using that? Maybe, is anybody working in that kind of field and has an opinion on that? Okay.
We are only using indexers, actually, to be very honest. It's
Okay.
just, I'm trusting the graph, and it seems to be very good. So I don't care about the events on my own. But it's sometimes convenient on the client side to just pause for recent transactions and pause the events out of something. But this is only really true for something you put on it, right? So if you interact with a smart contract, you have to read the logs to see what happened right now. So it's your return value. But this is unrelated to your question. Actually.
Yeah, exactly. So that was as soon as you would execute something on the chain after this event, it would work as before, right? It would just be stuff that's before.
As Web3 DApp developer, I would say. So just with the commercial background, I would say, I don't care about the blockchain itself. But this is not true for all the applications. It's just true for the ones that we have.
yeah, my feeling is the same. I mean, I spend so much time like finding problems in like event thinking code and all the things that could go wrong. But yeah, maybe people have different opinions. A different question that would be interesting, who is actually running their own blockchain nodes? Are people all using centralized providers to actually run blockchain nodes? And I'm not going to tell anyone, or is anyone like running their own nodes? I know it's a big hassle. Okay, yeah. I mean, it's awesome, but I feel like a lot of people don't want to do that because I have like horrible experiences, like data getting corrupted, and okay, the backups take forever, and yeah, my feeling is like I don't want to touch that stuff, which is horrible. But yeah, cool. Then yeah, I'm finished with the stuff I wanted to tell you. If there's any questions, would be happy to answer. Otherwise, yeah, I'm around to mingle later.
What's the current state of immigration? Have you already achieved that, or do you currently consider doing that?
So currently, I'm at the state where I actually generated a new block. I have imported it in another block, and I'm currently working on this, getting this snap sync to work. So I would say halfway. And yeah, we're currently at the state like where we're then discussing, okay, will people actually accept that when they lose all their events? Do we actually have to do something more complicated? I mean, then we could think about stuff like rewriting history if we want to get rid of all the other stuff, the historic things that are lying around. But yeah, I hope that we can find an argument that this is actually working good enough for people to accept it, to avoid spending more time on this. Yes?
Can you connect a bit to these migration tools? If I understand correctly, you're going to reach some off-chain consensus about the snapshot height at which one can calculate the state. Right? And then you're going to use your tool to calculate the new state root and, I guess, load DL2. And everybody, all the current validators of your I1 will kind of start. Oh, sorry, yes. So I will repeat then from the start. So just on this migration that you were talking about, if you can comment on how can you do this in a decentralized way? Because if I understand correctly, you're going to reach consensus about the snapshot height, calculate the state root with your tool, and then validators will start creating blocks on the L2 immediately, if I understand correctly, and then validate a posteriori that the state root that was like written in the regenesis block is actually correct. And then my question maybe is, how long does it take for your tool to actually calculate the state root? And would it make sense to rather have validators of the L1 each independently calculate the regenesis block and then move on to the L2 once there is consensus on that?
Yeah, a great question. So like the first thing you realized, which is important, to actually do this migration, we need to stop the chain, which is not something that I should have maybe said that, but actually we need to stop. We we ask for a hard fork at this block, then actually all the nodes stop creating new blocks. Everyone needs to run this migration tool. Might be faster or slower for people depending on their machine, and then we need to start it somehow synchronized again. So this is all like really much in discussion. So maybe an easier way is to start with a centralized sequencer in the beginning, say, hey, for this process, we do it, then we start it again, and then afterwards we have a second hard fork where we bring back decentralized sequencing, something like that. But this is something which is a bit like further on the roadmap. For now, I try to get this working with a centralized sequencer, which would basically allow me to get rid of that whole problem. It would be, okay, one node does it, then the sequencer starts again, and everyone else can verify if the block the sequencer uses as the new genesis block is actually correct.
Thanks. And maybe just to, if there are no other questions, to continue on that, in principle, do you really have to stop the chain? I mean, I guess once you fix the block at which you want to do the snapshot, the underlying chain the legacy chain, if you want, could continue forging, and if not enough validators, I guess, according to some rules.
Sure, that's always the option, right? That people say like, oh, I don't want to do this, I disagree with becoming an L2, I just continue the chain. That's possible. But if you would continue and you want to follow on the L2, then every block that's created after the fork date would be lost. So all the transactions that you send on the old chain, which is discontinued, would need to be reapplied to the other chain.
Right, but just to conclude my last question, which is actually where I wanted to get at, I was always curious, in these situations, you have a proof of stake system, right?
Mm-hmm.
So you have some sort of not in a stake problem, but actually between the L2 and the legacy chain, in the sense that if I'm validator, why should I stop forging on the legacy chain? Why can't I continue it forever and ever as a fork, if you want? Like a Silo Classic?
Yeah, I mean, you could do that. I mean, I hope that people agree that there's enough benefits with actually getting this like additional security from becoming an L2, like the additional benefits of being closer to the Ethereum Foundation, having easier bridging, that this actually convinces the validators to join that. But this is actually a task we have to do to convince them.
But you could do both, right? If it's proof of work, you can't because you have to split your resources, but...
Yeah.
Okay.
Cool, any more questions? Nice, then thanks for attending.